Yeah, today I'd like to talk about vertex algebra coming from for the n equals 4 superunion theory. So let me start with this remark by Bourdieu. So let X be a symplectic singularity. For example, you can start with a smooth symplectic variety. And suppose gamma is a finite subgroup of the automorphism of X, preserving the symplectic 2 form on the regular part. Then statement either the O before by gamma is automatically symplectic singularity. So in this way, you can this provides us a very easy way to construct a symplectic singularity. So, for example, you can do the following thing. So let gamma be your favorite complex reflection group. For example, while T of the algebra, semi-simple the algebra G, which is by definition generated by reflections in the defining vector space of the complex reflection group. So, for example, when while group, this is just a suburb of it. Then you can consider the cotangent to this vector space, which is just a direct sum of with its dual. And there's so this is clearly a symplectic singularity. It's a smooth symplectic variety. And there's a natural diagonal action of this finite group, and which preserves the symplectic proof form. So by this remark, the it's a defining vector space of complex H. This is H. Oh, sorry. Gamma. Thank you. And then by this remark, this O before, which is a spectrum of the invariant ring, is a symplectic singularity. And let me denote this in gamma. This is symplectic. associate. Boy, I'm writing down. And the fact is that if you consider n equal 4 for D, n equal 4 super Yang-Mills theorem, with gauge algebra G, and if you consider its Higgs branch, and this is known to be isomorphic to this symplectic singularity associated with this Weyl group. So if you want, and so this should be isomorphic to associated variety coming from this super Yang-Mills theory. So you want to, so if you want to construct this vertex algebra, you want to find construct vertex algebra whose associated variety is this symplectic singularity. And this is a conjecture by Bonetti Mene Lee Basti, which states the following. So you can consider any complex reflection group. Then there's exist vertex superalgebra, which I denote by V gamma, such that the its associated variety is isomorphic to this symplectic singularity. So in particular, so this one is quasi-this. And so this should be conformal. So this one is conformal. And so with central charge, so conformal means there's a action of a Virasoro algebra with certain central charge. And this central charge is determined by this from this complex reflection group. And the central charge.
You claim that there exists vertex operator algebra, which is V sub gamma, right? What is V acting GST?
This is a vertex superalgebra, so this is associated variety.
What exists? So for arbitrary gamma.
For arbitrary gamma, there is a vertex algebra satisfying certain.
What is V and some kind of symbol like epsilon?
Vertex superalgebra. Vertex. Sorry. Yeah, central charge is determined by gamma. So this is determined by the where so this is a this is a degrees of a fundamental invariance of this ring. So this is known to be polynomial ring. So it's generated by rank gamma generators, homogeneous, and the degree of this homogeneous generator is denoted by P.
Are these conditions wanted to expect it to characterize it, or there could be many?
It should be unique, yes. In general, they are vertex superprodukts. I didn't explain super, but so I'll explain why this should be super. So in a minute, I'll explain that. So that's what I'm explaining now. So this one is equipped with the n equals to 2 supersymmetry. In general, and actually it enhanced n equals 4 supersymmetry if gamma is a Cox. So this means more precisely. V admits the action of n equals to 2 superconformal algebra. With this central charge, or n equals 4 superconformal small superconformal with gamma. So little bit, please wait a little bit. I'll explain more. And so this one admits a free field realization. So in general, these vertex algebra are very complicated, very difficult to explain explicitly, but it can be embedded into a very easy vertex algebra, which is a beta gamma issue system. So this beta gamma stands for the affinization of wire algebra. So this is just an infinite dimensional wire algebra, and this part is super. This is affinization of threefold algebra. So this is infinite, Clifford algebra, infinite, right? So you can, so these are very easy, right? And so this one should be simple, and this embeds to this easy. If you do that, so.
That's your invariant with the gamma, and the super. Invariance, right? As the gamma, right?
No, this is just tensor product of dimension.
Okay.
Yeah. And of course, so this V gamma should be the vertex algebra coming from super Yamni theory for gamma equals to the while group. But their statement that so if you choose arbitrary complex reflection group, there might not be a physical theory, but still they conjecture there exists the vertex algebra satisfying the same property. And so this beam rusticity map is defined from for n equals to 2 superconformal theory to vertex algebras. But here we are considering subset of the theory which has n equal 4 supersymmetry. And so in this case, some of supersymmetry remains in the setting of vertex algebra, and you get a supersymmetry. Symmetry, vertex algebra. That's probably answers your who asked. Yeah, we asked. So this is a very interesting conjecture that for each complex reflection group that you can associate some kind of natural vertex. So this conjecture is still open in general, but you can do something for type A cubes. So this I want to explain from now. So the main reason why we can do attack this problem for type A is that we are in a lucky situation that the super, so that the, so G, yeah. So in this case, so I said that you can go from super Yamil theory, any 4D theory to 3D theory by so-called S1 compactification. And in this case, and take consider this map of beam rusted here, or you can consider a twisted vertex algebra here. And in this case, we are lucky situation that this diagram completes. And the gauge theory we get from super-Yamil theory is the Weaver gauge theory associated with the Jordan. So Jordan Weaver is something like this.
No complex interaction groups, just a sense.
So it's more convenient to talk about GLN case. So gamma is just a symmetry group. And this is just a CN. So by definition, M gamma is cotangent of Cn by the action of symmetric group, which can be identified with the overflow of C2 to N by symmetric group, which is just the spectrum of the surrounding N, Y1 to Yn. So symmetric group naturally acts on the index of the coordinate for both X and Y.
There are several versions. You can use different versions. You can minus, right? Beem, the second version must be direct. Prime tensor, minus, right?
So I'm
diagonal or diagonal. Naturally, this here it is like zeta tilde to minus one, right? To make it a symbol. Diagonal.
So you just change the index. That's most simple.
What about the action here and there, right?
So this is called the symmetric power of C2. So this is a singular space. But this is a very well studied object in mathematics. And so it's very well known that the singularity is resolved by the Hilbert scheme of points in C2. Of points and point C2. So this is, as I said, very easy to describe. This is consist of ideal in polynomial being of two variables whose codimension is n. And the map is for the so this is a resolution I'm seeing here. And this is a smooth swirl. And so what we want to do is we want to somehow attach vertex algebra naturally to this symmetric powers of C2. But it's easier to work on the non-singular setting. So what we want to do is attach a sheaf of vertex algebra. So what we want to do is want to to construct a sheaf V of vertex algebras on this smooth variety, and hope that its global section is the vertex algebra associated with the symmetry of group. And so there's a model for this kind of construction. So there was a work by Kashiwara and Ruki. So they constructed a sheaf of H algebras, or maybe H of H. So it's like a differential operators. It's very similar to the sheaf of differential operators, but because so this Hilbert scheme is not cotangent to something unless n equals to 2. We can't really talk about differential operators. So, which means you have to localize in the cotangent direction as well. So you cannot avoid considering infinite sum between the commutator for the commutator. So you have to consider some HRD completion. So this is some technical issues I don't explain the detail, but so this is for to deal with infinite sum. But you can make sense of such a sheaf on Hilbert scheme, which quantizes the structure sheaf of the Hilbert scheme of Hilbert. So maybe after H verb, this is okay. So this means this sheaf is a quantization of structure sheaf of the Hilbert scheme. And then a global section of this sheaf so I consider this the invariant part to get rid of each bar. So this is isomorphic to the spherical rational Cherenkov algebra. Associate symmetry group. So Cherenkov algebra appear everywhere. And it associated Grady is the global section of the Hilbert scheme. Yeah, maybe just all this one, which is identified with the function on the symplectic singularity. So this sheaf construction gives a very nice way of quantizing this symplectic singularity.
The difference between 1 and 3.
It's not immediate. Yeah. So you want to do their construction in the chiral set.
This question.
No, it's just a finite dimensional algebra.
Great.
I thought you wanted some kind of.
Yeah, we want vertex algebra. So we want to chiralize their construction. Just erased, but the construction goes as follows. So this Hilbert scheme is identified, is the same as the Nakajima variety. Or Jordan pivot, which means this one can be obtained by Hamiltonian reduction. So you can just do quantize Hamiltonian reduction. So for this quiver, you associate a vector space. So this is end of maybe I should not use 3 m Cn. So this represents this arrow and CNC, which represent this arrow. But in Nakajima's construction, you consider the double of the quiver. So what you do is you double the powers. So this is and so we have 2 matrices. And then CN and C2CN. So X, Y, alpha, beta, then this stands represent X and Y and alpha and beta. And this admits a natural action of G equals to GL. N, which is Hamiltonian. So you have a momentum to the algebra of this GLN, which is our Lie algebra, the durable Lie algebra, and the map goes like if you take bracket and maybe beta and alpha. So this is our momentum map. And for Hamiltonian, it looks like you consider the level set, which is a pre-image of the zero of this map, and then you consider the if you consider alpha and GIT quotient, then you recover the this symbiotic singularity. But if you do more carefully, by restricting the level set to some stable subspace, you recover the Hilbert-Scheme of the points in symmetry. So this is roughly Nakajima's construction. And then it's very easy to quantize this kind of construction. So Hamiltonian reduction is very algebraic procedure. So you basically quantize everything upstairs. So quantization goes as follows. So this cotangent vector space has natural quantization. Which is the wide algebra associated with this vector space, or the D module differential operators, global differential operators on the scheme. So this is non-commutative algebra. And so Hamiltonian reduction, you just replace Hamiltonian reduction by quantized Hamiltonian reduction. So as a level of functions, as a level of function, what you do is you consider the function on the level set, which is
Not real, correct? Beta L, right? Commutator, yes, well, beta L, right?
beta L. No, this is usual. You talk about the beta. This one.
Yeah.
No, this is related to the quantized momentum. No? So the Hamiltonian momentum map quantizes to the algebra homomorphism to GLN to this wide algebra, which is basically determined by this momentum map formula. And so this is what I want to say. So this is a quotient of the ideal generated by something like G, and you take a G invariant. And this kind of construction very naturally quantized. What you do is here you consider quotient of this wire algebra by the left ideal generated by the image of quantized momentum map, and you take a G invariant. This gives rise to algebra, which comprises this commutative algebra. And you can do this at the level of sheaf. And you get a sheaf of vertex algebra on the Higgs. You have to really be carefully because it's not really differential operators, but that's basically the story. So if you want to hierarchize this kind of construction, it's clear what we should do. So wire algebra. As I said, this has a natural affinization or chiral, which is just a beta gamma system. And then quantum Hamiltonian reduction. So you cannot really take this. So this kind of construction formula does not really make sense as a level of vertex algebra. So there's another way to do Hamiltonian reduction, which is a very old result by Costan and Sternberg. In 80s, so Hamiltonian reduction can be realized by a BRST reduction. So BRST reduction is kind of a mixture of homology and cohomology. And if you look at this formula, what you do for Hamiltonian reduction, you first take quotient, which is a homology, and you take an invariant, which is cohomology. So you first consider homology and then take cohomology. That's what Hamiltonian reduction does. But if you use BRST formalism, you can do this at once. It will be zero cohomology of the BRST cohomology. And then this BRST cohomology naturally chiralize. And so this will be BRS. Yeah, exactly the BRST cohomology, which is the semi-infinite cohomology. Introduced by Fagan. So it's actually relative, but not cohomology. I do not define this cohomology, but it's really analog of Chevalier complex for the algebra. So if you know Chevalier complex for the algebra, this is very easy to define. So there is a problem. So this cohomology can be defined so problem is that it can be defined only the hat action is at level minus n. So twice of minus of twice of critical level. And so this case doesn't satisfy this as a condition. So you cannot do this kind of realistic construction. So when work of Kashiwara and Ruki appeared, I thought about parallelizing their construction, but because of this obstruction, I gave up. However, the conjecture of Onetti, Meneghelli, and Russell says we should get super vertex algebra. So we should put super variables in some way, which means we should consider super variety. Parallelization is okay. Parallelization is so it doesn't really have definition, but so in general you have the following diagram. So vertex algebra, from vertex algebra we obtain by taking those six algebra we can take Poisson algebra. And the starting from plus, if you are given Poisson algebra, if you get the vertex algebra whose those six algebra recover this one, we say this is a chiral quantization of Poisson algebra or Poisson variety. But you can also take another factor of taking those algebra, which is algebra. And so in this, if you obtain vertex algebra whose those algebra, this one we say it's a quantization, and which is the case for. And it's a nice diagram. So if from algebra you go to for filtered algebra, you can take graded associated graded to get a Poisson algebra, and so we have the similar Poisson version of vertex algebra. And so this sits in the top of vertex algebra, sits top of the vertex algebra. You obtain all these classical opposite. So this kind of diagram we call hierarchization.
Right after the formula before.
So for this is for fine, but you can do other level of things. You restrict the open set and you can construct a preset and you can construct specification of subjects. Yes, that's a statement. Yeah. Yes. Usually smooth variety is easier to work for. Doesn't answer your question. Physical reason, if you go to 3D setting, you can turn on mass parameter to resolve the Higgs brand. So physically, you are doing such a. And in this case, you can do it because the diagram going to 3D. So somehow we want to consider some super analog of this quiver variety. And what we did was to consider this kind of super variety. you just replace the framing vector space by superspace C on one. So you replace this by C11 and do exactly the same construction. And then it's easy to see that such a construction does not affect the underlying topological space, and you get some sheaf of some super variety. Here on it's super, which is a scheme over the usual Hilbert scheme. Why we add the frame? So changing framing amounts to in the 3D setting, changing the boundary condition, if I understand correctly. So in the changing boundary condition should not change the representation theory. So that
only alpha will be sleeper. Commutator will be just old commutator, according to what you're right? No?
So
alpha and beta will be sleeper according to what I see, right? 1, 1, right? What about commutator? Commutator is just old.
So we don't change here. We only change here. Yeah. Plus you add one more. Yeah. No. Sorry, I forgot to write the arrow. So everything is the same except we are only here. The theorem which I did with
just will say that there is no direct definition like ideals or whatever, super ideals, nothing of this kind. It's just new object, right?
new.
Yes, super people, right?
Yes.
Yeah. No filter for that, right? Just new object organization of what we described. Right?
So yes, surprisingly, no one really studied super version of quiver variety. Yeah. So the statement is similar to the Kashiwara-Ruki. So there's a sheaf of HRD. So once this heuristic homology, so this choice of framing is chosen so that the BRST homology is defined, then everything you can do, as in the case of Kashiwara-Ruki. And you can construct a sheaf of HRD vertex algebra on Hilbert scheme. Such that the no, this super variety is as topological space. It's the same as the usual variety. It's just structured sheaf is super nice. So here it's the same. As a topological space, it lives on the usual Hilbert scheme. sorry, this is M. So this quantizes the arc space of the super Hilbert scheme. So you don't have time to explain arc space. We just affine version of the usual scheme, and it's quantizes the structure sheet. Yes, yes, yes. As a vector space, yeah, it's a vertex algebra over the formal series, but you need to assume that some compatibility condition with vertex. And then the global section is equipped with the n small n equal 4 or superconformal algebra with the right center of the charge. And so the conjecture on the existence of free field realization already suggests the existence of sheaf associated with the vertex algebra, because this kind of free field realization can be obtained by considering local section of the sheaf. So the natural restriction map from the to some open set. So there are some appropriate open set of Hilbert scheme. And so this is isomorphic to beta gamma BC. So it's a very locally a beta gamma BC system. Like the sheaf of differential operator is locally just a wide algebra. And similarly, this sheaf is locally just a beta gamma BC system. And associated variety is isomorphic to the symmetric power of sheets. And well, yesterday I said the character of, so this means this vertex algebra quadratis. And as I explained yesterday, the character. So in the super case, we have to replace by character by super character. But the super character satisfies the modular linear differential equation. And this doesn't really guarantee it's a quasi-modular, but in this case, you can actually check it's a quasi-modular form of mixed way. And this actually, as I express the formula, so I only write for n equals to odd. So this is given by so-called McMahon's multiple Q zeta problem, which is given by this nice formula. McMahon's. QZ volume. So this is a nice vertex algebra whose character is some multiple QZ. But maybe I should stop here today. And tomorrow I'll explain the class S algebra.